In Part 2, we'll learn about static equilibrium and how to use the magnitude and direction of forces exerted on an object and the resulting moments to predict whether an object will tip over when a force is applied to it. When an object is at rest, it's in static equilibrium and the forces are balanced. Static means that the object is motionless. Equilibrium means that the forces acting on the object are balanced with each other. Static equilibrium is an important idea to understand. Engineers want to design things that won't move or won't tip over when a force is applied to them. We wouldn't want a building to move or tip over when the wind pushes on it. And we don't want an adjustable desk lamp to tip over when extended over our work area. Can you think of other objects that need to stay in static equilibrium for them to operate properly? Think about a box sitting on a table. The box is in static equilibrium. It's at rest, and it will stay at rest until an external force causes it to move. This is part of Sir Isaac Newton's first law, which states that an object at rest will remain at rest unless it's acted upon by an unbalanced force. Engineers are interested in answering the question, will the object stay at rest if pushed on with a certain amount of force? Or, how much force does it take to move or tip over the object? Let's use what we know about forces, moments of forces, and static equilibrium to answer that question. If an object is in static equilibrium, the forces that act on the object in the vertical direction are balanced. Forces that act on the object in the horizontal direction are balanced. And all of the moments of forces acting on the object about any point are balanced. We can use equations to represent static equilibrium and balanced forces. The sum of the forces vertically is equal to 0. The sum of the forces horizontally is equal to 0. And the sum of moments of forces about any point, P, is equal to 0. Let's see how these equations apply to the box resting on the table. What would the free body diagram look like for this box at rest on the table? Make a quick sketch of the free body diagram. Gravity is acting on the box, so we need to show a weight vector pointing downward. Assuming that the mass of the box and its contents is evenly distributed, we can assume that the center of gravity is at the geometric center of the object, so the weight vector acts at the center of the box. The table is also resisting the weight and exerting a normal force upward on the box. If the box weighs 7 pounds, then the normal force also equals 7 pounds. The two forces are equal and opposite to balance each other. No horizontal forces are exerted on the box as it rests on the table, so the second equation is satisfied. Now let's think about the moments on the box resulting from these two forces. If the box is in static equilibrium, the sum of moments of forces about any point equals 0. Let's choose the lower left corner of the box and call it point P. It doesn't matter which point we pick, but point P will be important when we talk about tipping the box. Now let's sum the moments about point P. To find the magnitude of the moment caused by each of the forces, we need to know the magnitude of each force and the perpendicular distance from the point to the force. The box is a 1.5-foot cube, so the length, width, and height are each 1.5 feet. Since the mass of the box is evenly distributed, the center of gravity is in the geometric center of the box. So, the perpendicular distance of the center of gravity is 0.75 feet. The normal force, N, will cause a counterclockwise moment about point P, so the moment that results is a positive moment. On the other hand, the weight, W, will cause a clockwise moment, so it is negative. Calculating the moments caused by the normal force and the weight, we find that the sum of moments about P is equal to 0, and the moments about point P are balanced. But what if we push sideways on the box? You can push at the top of a box with a horizontal force without moving the box, especially if the box is heavy. As long as the box doesn't move when we push it, it's still in static equilibrium. That means that the forces exerted on the box are balanced. A frictional force between the box and the table will balance the horizontal force that you apply to the box. When you push the top with more force, the side of the box that you're pushing on begins to lift up, and the location of the normal force begins to shift. If you continue to push until you increase the magnitude of the pushing force enough and keep the box from sliding, the box will eventually tip over. What is the force that causes the box to tip? We'll call this the tipping force. Let's sketch a free body diagram of the box under an applied horizontal force like we've been talking about. We know the weight and normal force balance each other in the vertical direction, but now we're adding an applied horizontal force, force T. If the box isn't moving, there has to be a force that is equal to and opposite of T. Where does that force come from? The force that's acting opposite to the applied force, T, is the frictional force between the table and the box. Sometimes the friction isn't enough to keep the box from moving, and with enough force, the box will slide. But as long as the box doesn't move, the magnitude of the frictional force will always balance the applied force T. If the box doesn't move, the more force you apply, the greater the frictional force. If there is enough friction between the box and the surface, you can push on a box with enough force to tip it over. What happened to make the box tip? What caused the box to move? As you increase the applied force T, the box begins to lose full contact with the surface, and the normal force N moves to the tipping edge. The tipping edge is the only part of the box in contact with the table surface as it tips. Before the box tips, it's still in static equilibrium. At this point, the vertical forces are still balanced, the horizontal forces are balanced, and the moments about point P are balanced. The critical instant occurs just before the box tips, when the bottom of the box barely lifts off the surface and the normal force is exerted on the box at the edge in contact with the table. Any minuscule increase to the applied horizontal force will cause the box to tip over. At this instant, the applied force T becomes the tipping force. We can use the static equilibrium equations to calculate the critical tipping force. Because the box is in static equilibrium before it tips, we know that the normal force is equal to the weight and the frictional force is equal to the applied force at the critical instant, which we called the tipping force, T. But we don't know the magnitude of the tipping force. We can use the sum of moments equation to find the tipping force. First, let's add dimensions to the free body diagram. The box is a 1.5-foot cube. Let's add the magnitude of the forces we know. Now we can sum the moments about point P. The perpendicular distance from point P to the normal force N is 0, and the perpendicular distance from point P to the frictional force F is 0. The perpendicular distance from point P to force T is 1.5 feet. T will cause a counterclockwise or positive moment. The perpendicular distance from point P to force W is 0.75 feet. W will cause a clockwise moment, so it will be negative. Let's simplify the equation and solve for T. You'll use this formula in a class activity. Write it down and be sure to identify the variables. If we substitute the values we know and solve the equation for T, the result is T equals 3.5 pounds. We have our answer. If you push this box and the box doesn't slide, it will tip over if you apply a force, T, that's greater than 3.5 pounds. If we push with a force less than 3.5 pounds, the box stays in static equilibrium. The formula for tipping force is a mathematical model that is based on an accepted law of physics, Newton's first law, not on data. We call this a theoretical model. Think about the box experiments you performed in class. Review the mathematical model you derived to represent the magnitude of the tipping force required to tip a box. This is called an empirical model because it is based on experimental data. Does your empirical model support the theoretical model? The data you collected in your experiment and your empirical model should support the theoretical formula for tipping force that we just derived. To review the series, you first learned about types of forces and how to represent forces that are exerted on an object in a free body diagram. You also learned that forces on an object can cause moments that tend to rotate the object. Then we explored the idea of static equilibrium. You learned that an object in static equilibrium is at rest and that the forces on that object are balanced. Using the equations of static equilibrium, you analyzed the forces exerted on an object that's in static equilibrium and derived a theoretical formula that can be used to calculate the amount of force that's required to tip a stationary object about its tipping edge.